Okay, we are recording. So let me hand things over to Sim One, Group 436G.
Hey, good morning. Hope everyone's doing well. Thank you for taking the time to join us this morning for our final presentation. We look forward to hearing your feedback at the end. We are the 7 years, and this is our product, Sim One. First, we would like to briefly introduce ourselves. So, our team consists of 7 engineers, a few mechanical, a few aerospace, and a few double majors. My name is Ryan Flickinger, and I primarily support the team in mechanical design and assembly.
My name is Leonardo Aragoni, and I worked on CAD development, CAD design.
My name is Nicholas Dellinger, and I also helped with the CAD development.
My name is Ricardo Garcia. I was in charge of purchasing all the parts we needed to order and also the bill of materials.
Hi, I'm Colin Hall. I was responsible for the drawings and electrical assembly.
Hi, I'm Simon Hu, and I was the coding specialist for the team.
Hello, I am Kyle Karamahalis, and I was in charge of all things testing and manufacturing.
So first, a general outline of our presentation today. We will begin with an objective that led us to actually building this project. And then we're going to go into a general product overview to establish some familiarity with our solution. We will then briefly touch on the specifications of our system, such as the maximum speeds we're able to achieve. Then a breakdown of our testing procedures will follow. Next, we will highlight the key features of our design that make it unique. And then we will move into detailing the evolution of our design throughout the semester. After that, we will cover our product's cost breakdown. And lastly, we will move into summary and conclusion. So for our objective, I'm going to hand it over to Leo.
Yeah, thank you, Ryan. So our main objective for the project was basically so we could build a shaker for a microbioreactor, so we can assess obviously the proper cellular properties and larger volumes, and so we can make one that's better than the one that's in the market right now, right? And obviously the shaker table is the most important component of bioreactor, right? So because it is responsible for proper culture and prevention of any micro sedimentation. So kind of want to make sure we hit those points when creating a product. And I guess the main thing that we went for was also simplicity, right? So making sure that our product was simple and robust and as adjustable as possible for the consumer. So making sure, I guess in translation, we just want to make sure that we could hit the 3 main points that we needed, which was obviously make it linear patterns, making orbital patterns, and making double orbital patterns. And then using those 3 points, how can we, I guess, make it as robust as possible in a mechanical way, electrical way, and then also in a coding perspective. So we kind of just wanted to dumb down the product to make sure it was easy for the consumer, but also to manufacture and kind of assemble it, put it together.
So to start with a high-level product overview, our final product measures 0.3 meters long, is 0.2 meters wide, and it's 0.15 meters tall. The total weight, including all the electronics, is 4.06 kilograms. So the overall design, we broke it down into 4 critical sub-assemblies. We have the aluminum base assembly, a linear actuation assembly, the orbital rotation assembly, and the well plate holder assembly. So the linear actuation assembly critically relies upon a Scott yoke mechanism to achieve its motion. The orbital rotation assembly relies upon motor mechanics. So I'm going to dive into a little bit more about the base here. So the base consists of 7 6061 aluminum metal pieces. These pieces are held together with stainless steel hardware. We selected stainless steel over steel for its corrosion resistance because the design is going to be used within the lab. A single NEMA 17 motor is attached to the shorter stands on the left of that render. The taller stand on the far right of the screen supports 2 linear guide rails. If you look closely, you'll see a series of small holes, and those are the mounting holes for the rails. We ended up settling on this design because, as you can see in the center of the base, it's pretty open, so any optical analyzing could make it in place there. Additionally, there is a silicone base attached to the bottom of that plate, so to minimize any vibration, and we ended up kind of lowering those stand heights to bring the center of gravity of the whole design as low as we could. So a little bit more about the linear actuation assembly. We settled on a Scotch yoke mechanism to achieve linear motion because of its simplicity when we compared it to other options of achieving this kind of movement. So the ball carriage rails act as rollers, so they support this rectangular plate in the vertical direction, but allow it to move freely in the horizontal direction. And the Scotch yoke mechanism converts the rotational motion of the wheel into linear motion. So a single NEMA 17 motor drives a wheel, and from that wheel there's just an extruded pin, and this pin is confined to a slot in this rectangular plate. So for every 4 rotation of the wheel, the plate moves there and then back again. For the orbital rotation assembly, there are 2 free spinning cams which are press fitted into roller bearings within the top plate, which you just saw. The third cam is fixed in the NEMA 17 motor. So when it's driven, it rotates in a circle. The last subsystem, which you will see soon, is the tray holder. So this tray holder has bearings for all 3 of these cams we press fit it into. And this fixes the cams in relationship to each other, so they can only rotate parallel to each other. So the tray holder was planned to be milled from HDP, high density polyethylene, but we ended up 3D printing it from PLA for our testing procedures. HDP was selected due to its chemical and heat resistance, as well as its low cost and durability. So as mentioned, there are these bearings within the tray holder that the cams can press fit into. If you look closely, you're going to see there's spring plungers on the walls of the wheel plate, and these allow our wheel plate or test tube fixtures to be held snugly in when they sit down. So there's 2 levels here. The lower level is for the wheel plate, and the top level is for the tube trays. And as you can see, we left kind of the bottom of it open again, so any optical equipment can be placed below it.
Okay, so for our electronics and controls, so we have 2 NEMA 17 motors. And so in order to control these motors, we needed to use, 2 A49888 motor drivers. And so all of this stuff is going to be powered using, an Arduino Uno, and all of the information from the Arduino is going to be displayed on, we have an LCD screen that is attached to it. And then also we have the capability for 2 encoders to be attached to our Arduino as well. So the entire system is powered using a 12-volt power source that is used to power the motors. And then the 12-volt power source is then stepped down using a voltage regulator to power the Arduino. So the total power draw of the system is going to be 49.2 watts, which we've confirmed that works with our power source. And yeah. Okay, so as for the code that controls the system, so it is less than 250 lines of Arduino code. It's overall a pretty simple code. It doesn't use any libraries. It doesn't use Excel step or anything like that to control the motors. Instead, what we did was we used we told the motors to turn on for a certain amount of time and then turn off for a certain amount of time. And then we set the direction that we want the motors to run. And this was supposed to increase the speed at which the program ran at, so that there was no issues, which we did run into some issues earlier with the libraries and with other things where the code was not running quickly enough. And so the motors had a maximum speed of like 100 RPM. But then we reduced the use of libraries and other stuff, and that allowed it to increase in speed to read, and now it's capable of reaching the maximum speeds that were requested. So the code is capable of running the shaker table for up to 2 weeks at the maximum required speeds. And if you hold a button at any time during those 2 weeks, any of the 4 buttons that we have, it'll stop the program. And we've tested this extensively, and it's worked, every single time. And we also have encoder capability built into the code. The encoders aren't currently being used because of issues that we had during testing, so it's commented out. But there is capability for encoders to be used in future versions of the shaker table. As well, it also displays the, on the LCD screen that we have, which is located in our like our controller. It displays the current speed and time. So what it does is it displays the amount of minutes that it's been running for, and then once it reaches hours, it's going to display the number of hours instead that it's been running for, and then it will always display like the current RPM that you set it to run at.
This is our interface. Our design features a simple 4-button digital interface. The buttons adjust the pattern, time, and speed. The time button increases every time you press it by 10 seconds. But if you hold the button for more than 5 seconds, it increases by increments of minutes. And if you hold it for more than 20 seconds, it increases by increments of hours. Pressing the pattern button will cycle through the 3 patterns that the shaker table is capable of. And the speed button, pressing the speed button increases the RPM by 10. Once it reaches the highest RPM possible, then it'll cycle back down to the lowest possible. Once the program is set, you would press the start button and the shaker table would start actuating. Like Simon said, holding any of the 4 buttons down for more than 3 seconds will have a program stop. But if there's an emergency or entire power needs to be shut down from the system for some reason, you could flip the emergency shutoff switch, which is featured with the LED.
Now I'm going to go over the system specifications. These specifications were given to us by the UF Biofoundry lab. And the main gist of it is that they're supposed to move in an orbital, a linear, and a double orbital pattern. For the orbital pattern, they're supposed to be adjustable with speeds up to 350 revolutions per minute. And the orbits themselves must be up to 25 millimeters in diameter. For the linear movement, it's supposed to move at 350 cycles per minute as well, with a distance of 25 millimeters traveled. For the double orbital, it's also 350 cycles per minute, with a movement of 25 millimeters around about the major axis.
So our first major round of testing was on November 14th. And on this day, we demonstrated to our teaching assistant, Alex, that our prototype can stand without human intervention. We showed a completely soldered perf board, finalized code, and that our prototype can self-sustain operational states of linear orbital and double orbital shaking patterns. Our second round of testing commenced on December 1st. And in this testing, we ran our shaker table and were able to determine the maximum speed of our linear shaking pattern was 250 RPM, the orbital 350 RPM, and the double orbital 200 RPM. We also were able to run all 3 of these shaking patterns for 2 hours.
Yeah, I don't know if you guys can see the video there. It might be a little bit choppy for you guys, but that is the orbital pattern.
Yes. And these are videos of our shaker table running in the linear pattern first. On the left And then on the right is the double orbital shaking pattern.
So our design has two major highlights that create the linear and orbital motion of the shaker table. The first design highlight is the Scotch yoke mechanism, and that's responsible for the linear motion of the shaker table. And the second design highlight is the 3-cam orbital rotation system, which will create the orbital motion. As mentioned previously, the Scotch yoke mechanism is used to convert the rotational motion of the NEMA 17 motor, which is attached to the bottom of the U-shaped base structure. And that converts the rotational motion into a linear movement of the main shaker plate. A flywheel is attached to the motor shaft on top of the U-shaped base structure, and this is done through a set screw. And this is primarily to reduce the slippage of the motor shaft and the flywheel attachment. The flywheel also has a track roller bearing, which is on the outer rim of the flywheel itself, and that fits into a slot on the shaker table. And as the flywheel spins, the track roller will push the actual shaker table in the linear motion. And on the other side, the other U-shaped base is the two linear guide rails. And these are necessary to create this linear motion. So as the flywheel rotates, the shaker table will glide on these rails relatively frictionless to create a smooth and linear motion. This robust design allows for easy scaling and is also leads to a pretty relatively simple manufacturing process. So the second design highlight of our design is the cam system that we have. This cam system is responsible for the orbital motion of our shaker table and is also able to permit a pretty steady rotation without vibration. The cam system consists of 3 cams, and 2 of these cams are freestanding cams that press fit into 2 bearings on both the shaker table and the tray holder above it. The last cam is attached to the NEMA 17 motor shaft that is bolted onto the shaker table. And this is also done in a similar fashion to the flywheel, where the cam is press fit onto the motor shaft and a set screw is used to reduce the slippage of this attachment as well. A key feature of this is the cams are easily replaceable. So if we want a different orbital radius, then we could switch out the cams with longer or shorter ones to change the radius of motion of the orbital pattern.
So yeah, now I'm going to go a little bit into the evolution of our design. Obviously, we had our first original design over there on the left, which was very large in comparison to what we kind of like went to, as you can see on the right. So I guess the biggest change that we had was obviously number one was material. We changed up the material a lot, and then also, like I said, the size, right? And the main reason for that was because we originally had it made out of sheet metal, as you can see over there on the left, and that made it super kind of like hard to manufacture because that is very thick. That's a very thick plate, and we kind of didn't have the tools to really make those bends in house. So we went to a more, I guess, robust design with the U-shaped base made out of 6061 aluminum, as you can see on the right. That, as you can see over here, so these bases and then the base on the back over there. It's basically comprised of 3 parts, right? So there's 2 side pieces and then 1 top piece that is secured by 4 fasteners. Those are basically adds a lot of stability to our product and overall component, and that's mainly because it's also connected to the motor, right, and the linear rails in the back. So also to kind of avoid any larger moments, we also kind of shrunk it down a little bit. So we lowered it. We lowered these bases and the base in the back, so we can kind of avoid any like large moments that we would have while the product was on. So that really helped us in the end, especially when we started testing. So that was a very large change. And then another huge change for us is the tray design. So we went basically from a tray design that had about 10 components to a tray design that had only like 2 components. So that was not only like kind of a victory in terms of how much cost is into these things, but also the simplicity factor that I mentioned earlier. So I think as Ryan mentioned earlier, we had these ball spring plungers that go on the side of the tray holder, that those kind of secure the well plate and secures the also the tube rack. So it's super easy, it's easy also for whoever's using it, right? So you don't have to like detach it with these bike locks. It's kind of made it simple for everyone really. And then another like big change that we had was the base. So we kind of went from just a base that was made out of rubber, as you can see on the left there, to a base that is made out of aluminum with an anti-vibration mat under. Once we added that anti-vibration mat, it just made things so much smoother for just whenever we're running any pattern. It really made like a huge change and increased stability, very little vibration, and was also like a very I guess a good victory for us. And another small change that we made that's like not mentioned I guess in the slide was the flywheel. The flywheel had a little change in terms of I guess its purpose, but we went from like a block to like an actual circular flywheel right here. And we had to, in our prototyping phase, we had to like change a little bit of where this guide pin was placed. So we just placed it a little bit closer to center because originally our design had the rails coming off a little bit over here when we started the scotch yoke mechanism, but that was fixed after prototyping and testing. And yeah, I guess kind of worked out for us again. So those are the main, I guess, changes in terms of mechanical components. I guess I think Colin will go over the electronics.
Yes, so the electronics underwent a lot of evolution as well. So the initial prototyping was done on a breadboard because breadboards are non-permanent and you can easily replace components and wires. Additionally, breadboards have built-in voltage dividers for a shared voltage and ground, which becomes much more complicated on a perf board. But once the design was solidified after numerous testing events, we moved to the perf board. So perf boards are advantageous due to their semi-permanent nature. Wires and components will stay in much sturdier with solder. And while that is advantageous for most components and wires, we made sure to use inserts for the motor drivers because in the case one gets fried, or if we just have to replace one for some reason, you can easily take them out of the inserts rather than unsoldering every pin, which is, I think they have like 16 pins. Additionally, the perf board is a much more clean and condensed version of the breadboard. In the perf board design, we utilized copper wires instead of soldering tunnels because soldering tunnels can become really messy and it takes a lot more time and precision. But if you wire them with copper wires, as you can see, it makes the perf board look a lot more condensed and professional. Additionally, through the evolution of the electronics, we integrated the voltage step down because when we were using the breadboard, we were using our laptop to provide the 5-volt voltage for the Arduino and other components that required 5 volts, such as the LCD. But we encountered groups that actually fried their computers or their ports because of a miswiring and using their computers. So we were glad We were happy to switch to the voltage step down when we integrated our perf board.
So now I'm going to go over the cost of this assembly. So to replicate this exact assembly, it would be $715.28. And although this sounds like a lot, we did not actually spend this much either. I just tried to document the exact parts that we had, and some of them we got straight from the lab. So one of the NEMA motors, I tried to find the exact model and it was like $160. So in reality, for future purposes, we could probably find like a $40, $50 one to replace that, which would lower the cost significantly. And the major contributors to the cost were the two NEMA 17 stepper motors and the linear rails. The linear rails alone cost the assembly $317.88, which is kind of ridiculous, but that's one thing we can improve in the next design. Probably get bigger rails, which are cheaper. And the wholesale cost of this assembly would be $551.45. And in this calculation, I considered replacing the $158 motor with like a more reasonable one that has the same specs. And also we had a bunch of packs of fasteners that cost a lot up front, and they have way too many fasteners than we require. So I just divided the cost out for the fasteners for each assembly too.
So our assembly was relatively easy and straightforward. Our assembly only requires screws and press fits. And from beginning to end, it would take roughly 26 minutes to assemble. The manufacturing cost, the total cost came out to $203. We landed on a price of $14 per hour, as that is what a teaching assistant is paid. And we have our 6 parts here, the quantity that we use in our assembly, the manufacturing time, the total manufacturing time based on the amount, the quantity that we actually use, and their cost.
Okay, so for future designs of our shaker table, we want to, as Ricardo already mentioned, we want to use bigger linear guide rails because they should reduce the cost. As we were saying, they cost over $300 for just 2 of them. And they would also potentially increase the rigidity of the linear motion. The next thing that we wanted to maybe do is when we were testing, we found out the linear motion could only go 250 RPM instead of the desired 350 RPM. And we think that this is because the stepper motor that we currently have is just not capable of moving that weight, the weight of the tray table and the plate that quickly. And so if we use a stronger motor, it could potentially be able to drive the linear motion at the speed that we want. Next, also in order to potentially improve the linear speed, but also just decrease the amount of moments that we have, reduce the number of vibrations, is we want to make the Scotch yoke plate from lighter material. Having a lighter material, the Scotch yoke plate is probably is the heaviest part of the entire thing. The tray table is very light, and the cams and everything else is pretty light. So reducing the weight of the Scotch yoke plate would really allow us to make our linear motion better.
Yeah, exactly. And another thing that I kind of want to add there too is we already had the capability of adding an encoder, but in the future we definitely add a magnetic encoder for this purpose. And so just so we can see like where what kind of positioning we really want to make it even more precise.
And the encoder could also have the capability of a program shut off if something gets stuck while no one is present physically. And then in summary, the Sim1 shaker table developed by the 7 years meets the requirements from the customer at a competitive price with a sleek design. The shaker table can safely and consistently reach the target RPMs for linear orbital and double orbital for extended periods of time. Future iterations will feature more powerful motors, bigger rails, and in the manufacturability, we will increase the tolerances on our drawings to reduce the slop and increase the overall efficiency of the system. So please get ready for our next iteration, Sim 2. Thank you all for being here and joining us for our final presentation. We will now answer any questions you have for us.
All right, thanks. Questions from Dr. Nemi or Alex?
I guess I'm gonna jump into it. So good presentation overall, guys. I just guess, and I've noticed this with a couple of groups, and you're just now the first ones I'm poking about it. So don't take this as me coming out of the gates and roasting you guys hard. You explained the progress and the process and kind of how you went through things. But I didn't see a whole lot of engineering in an engineering presentation. You know, you talked about change you would make and how you would want to improve it, but where are the calculations to show how you're going to size the components? Why do you want to move to a NEMA 23 motor? You talked about it, but there was no torque calculation to show that it was actually the better case. You know, that's just one example here. You talked about slop. Where was some testing to show how much slop there would be? And, you know, can you get rid of it by moving to larger linear rails, or are all linear rails going to have that much deviation? You know, and again, like, I'm coming out after you guys because you're, I think, number 3 that I've seen this with, where it's just like, there's not a whole lot of engineering there, and it would have been nice to see. I know you guys did it because I yelled at you about doing it. Why didn't you show it? You know, other than that, I don't really have any questions. I saw this evolve throughout the semester, so I know where you guys are at, and I love your tiny little adorable linear rails. They're the greatest. Don't get rid of them. It hurts me that you want to get rid of them.
Thank you for the feedback.
Yeah, I mean, we're just trying to get rid of them because of the cost, but yeah, I love them too. We all love them. Ryan loves them the most, I think.
Yeah, and so on the point of cost, you said it was like, what, $750? Can you go back to that slide? Now we will get a question. So 3/4 of your cost is in the motors and the linear rails, but total cost is only $715. How does this compare to other products that are on the market?
Yeah, so I think it is a little bit on the high end. I'm not too familiar with the cost of the other shaker tables. I'm not sure. I think Ricardo might have done some research on this, but in terms of how we can even, like, we just kind of wanted to make this as, like, in terms of like a consumer, I guess, where you can just kind of buy something that's like off the shelf. It's like, okay, easy, like that's a no-brainer kind of thing. So we just think like 715 is a little bit on the high end, but we're just trying to make it the cheaper as possible, I guess.
Yeah, and I know for some wholesale pricing, a lot of groups went to like AliExpress and got everything at like the very minimum price, which kind of like staggers it very extremely and it's not realistic. And all of our parts that we estimated are just off McMaster. So it's going to be the same quality as all of the other parts that we have now, and there won't be any variation.
And I'm gonna send you guys a link real quick here. This is probably a higher end device, but
So I think we're good on the pricing then.
This is just a single example, but again, we're talking about the price and wanting to bring price down and cut cost. Do you need to? If you were to find this device and add even $250 to the cost and make it $1,000 device that you could sell for $2,000.
Yeah, I guess we're just thinking of like making it as like much profit as possible, but
I understand and this is now, this is the fun part. This is where I really get into design. It's like, you have to make design decisions. Typically, a lot of design decisions get made because of cost concerns. But as engineers, we also have to ask, is cost the concern that's driving this design decision, or is it an actual design decision that I'm making? Like, is it penny pinchers yelling at me that I'm too expensive, or am I just going to make slightly less money at the end of the day to have a more robust product? And that's a question that we have to ask ourselves. So you have to know what you're competing with or competing against.
Right.
So Alex, did you have questions? I'm done beating up on these guys.
Yeah, absolutely. Well, actually, honestly, I have more compliments than questions. Firstly, I just want to say that I think this is so far has been the best structured presentation. I think what we were sort of running into and experiencing with the other groups is that, when we post an outline about what the presentation should be on, it kind of turns into this like high school feel, like, here's what our presentation's about. We're going to go through this section 1, right? And so I felt like this was the one that, although it followed that outline, didn't like speak to that outline and actually felt like a real presentation on a product, which was a great refresher. I just want to commend you guys for that. Secondly, I also am extremely impressed that you managed to get this thing down to, like, what you said, 250 lines of code, which, at least from what I've heard around the other groups, is kind of an anomaly. I've heard hundreds, if not thousands, of lines of code from the other groups, and I wanted to ask how you managed to do that, and if you have any idea why or how you managed to get it so short.
I think a lot of that actually comes down to our design. Since our design is just, it's pretty simple. We're just like other groups, they have to like kind of diligently be like, oh, we have to make a circle. Our orbital motion is pretty much already a circle. So especially for orbital motion, it's like, I don't know, like 6 lines of code to make orbital motion work, because we already have that orbital motion built in. So we don't have to, have 2 different axes and figure out how that makes a circle, and then anything like that. As well, I think, hold on, let me pull this up real fast. Okay. Yeah, as well, I spent a lot of time working on the code and trying to cut down the number of lines that we needed. So I replaced a lot of the things in here with I looked up like different methods and whatnot of making sure that the amount of code was decreased, especially because we were running into these issues with the speed. When we started testing, we found out that we couldn't go over 100 RPM, but after messing with the code a lot and deleting a lot of the extraneous stuff and coming up with code that runs quickly, it ended up being relatively short. And then I think the last thing I'll mention about this is that our control system as well is pretty simple, since it's just the 4 buttons. It's really only like 30 lines of code, I want to say, to control all of the things and to get the motors started and running. So I think all of that together makes the code just really short. And when we're going to upload it with all the comments and stuff, and I think that'll help explain it even better.
Wonderful. But so you actually took the time to attempt to shave down the number of lines of code.
Yeah, I did.
Well, that's wonderful. I don't think many of, if any of the groups did that. So I'm sure that the future Mech 3 students will very much appreciate the reduced code so that it's more intuitive to look at. I did have a concern about how you managed to get the motors to run without the use of libraries. So I assume that that looks something like a while loop that steps or at least sends a pulse and then has some delay that inherently controls the RPM based on how quickly that while loop is looping.
Yeah.
Something like that. So
Yeah.
my biggest concern with that is that if you start this loop, you send a pulse, and then you delay. That at the surface level is good, but there is also time spent in that loop to do anything else you're doing in that loop. And then the time it takes to get back to the start of that loop is inherently dependent, and the time that it takes to send the pulse is inherently dependent on the speed of the processor of the chip. So it's very possible that in future renditions of this project, if for whatever reason, may it be a cost decision to either go to a cheaper chip, or maybe you want a faster chip, if the speed of the processor changes, it may unintentionally affect the output RPM of your system. And I was wondering if you had thought about that at all and what you plan to do to combat that.
So yeah, that's, I guess, one of the future things that the encoder code that I program can do, because it'll actually when it's actually implemented in, because I took it out because it wasn't working with the testing at all. And it was just going to take too much time to try to get all of them working together. But in the future, with a little bit of extra work, we could get the encoder, and it will, what you would have to do, which I guess for future, if you change out the chip, you'll have to run the code and then use the encoder to verify how fast that the shaker table is running at. And then when you've done that, you can just edit the delay to align with what what we did in our thing is we didn't use the encoder. We just verified it visually using like a slow-mo camera and seeing how many times it's rotating, and then we plotted that on like an Excel chart, and then we created an equation that fit that curve, and then we used that as the to figure out what time delay was needed in order to run a certain speed. So you would have to do that, but it would be faster because the encoder would just tell you how fast it's running.
Right. So effectively, you're creating a closed loop PID controller out of an encoder.
Yeah.
Okay, wonderful. That's a good plan to have moving forward. And I think you should absolutely document that and make that very clear that could be a future problem for future students. Great. Dr. Traum, if you would like to take the question that I have been stealing from you yesterday, you're more than welcome to. Otherwise, I can ask it.
Oh, it's okay. You can ask it.
Okay, wonderful. So the last question that I have is not meant to be a trick question at all. It's a genuine question. But after going through the design, manufacturing, and testing process of seeing this design in real life, and also observing some of your other designs around you that your other fellow students have made, do you believe that this design is truly the best design to meet all of the customer needs and effectively, perform them the best? Or do you think that there is a different design among the other designs from your fellow students that may be better, more suited to actually suit the customer needs?
Based on what I saw, our hedgehog concept really played out to be more valuable than we expected, because we do feel like we have the most simple design. We have the motor creating the orbital rotation, and then with the Scotch yoke, we have one motor creating the linear, and it avoids all of the XY. If you use a belt or guide rails or sets, what are they, lead screws? All of those designs function much slower and require a lot more work and at the end of the day, our shaker table performed exactly what the customer needed, and I think it is the best and most competitive one out there. I would love to have another group member chime in to add to that.
Okay. I think that, yeah, for certain things, I think that our design is very good, especially the simplicity aspect. I mean, that helped the design helped with the code, made the code a lot simpler. It will make it a lot easier for future groups to debug. But I think that one of our flaws is that for the adjustable orbit and yeah, we would have to manually go and replace the cams, so that is a weakness of ours. So I think that we are definitely good at certain things, but there are weaknesses in certain areas. So I can't say for sure that ours is definitively the best if you rated the orbital motion very highly, the adjustable orbital motion very highly. But if you rate the other stuff highly, then I think ours is definitely very good.
Yeah, I absolutely agree with that sentiment. I think that this design is one of the better designs out of the set that we've seen this semester. And interestingly, I think that this is a very unique design compared to what we've seen this semester. I think that this design excluded every design had some other team where it was like very close. There were usually, you could like kind of group them into pairs or sets of very similar designs. But with this one, I think there was enough unique components to where it really just kind of falls into its own category. And so it's very interesting to see how this one works. And I think it's great. I think this will definitely be a solid contender for what will eventually be the single settled end product.
Yeah, I don't think
So
anybody else did a Scotch yoke.
there was one group
one
that
other group.
tried, but they didn't have any linear rails with their Scotch yoke.
Should we fill out a patent?
No. No, well, that's, I wasn't going to ask, but since you brought up patents, here we go. So Dr. Nemi asked a couple of questions that I think were good about, understanding the market and identifying, the price point of your shaker table as a finished commercial product versus competitors that are already out there. What about intellectual property protection? The reason I ask is because we had one group that I think might have crossed the threshold into a mechanism that's patentable. And I actually suggested that they reach out to Rick Crowley and confirm my suspicion. But I don't think there's anything here, right? It's Scotch yolks and linkages and things. There's nothing here that I think could be patented, and maybe that's harsh or wrong, but given that somebody, a competitor, could just buy your shaker table and unscrew it and look at how the internal bits work, and then provided they don't have Matt Trom breathing down their necks about not buying stuff on Alibaba, buy stuff from a less expensive distributor and now produce basically a clone of your shaker table at reduced rate. How do you guys prevent that sort of copycat, right? How do you stay competitive in the market, given that I don't think have anything here that can be patented? If you open the case, it blows up.
Our business model could just be for like a year or two. Sell as many as possible and then expect people to copy it, run out with the money.
Yeah, I guess it's like it's a W in terms of like, it's a win in terms of yeah, we made our design super simple. It's like easy to like put it together, but it also hurts us in terms of what you're saying, right? Where it's like, it's even so simple that like anyone can just like I guess buy it off or copy it. So it hurts, but it's also a good thing in terms of that simplicity aspect or hedgehog concept that we had.
So I'm hearing the solution is get big fast, go out there and sell as many shaker tables as you can, develop a reputation. And now even if everybody else comes along with identical shakers, you guys have got the brand recognition and the market penetration that people just, buy yours because they know your company and they know that your shaker is a high quality product, but nothing that prevents somebody from coming along and copying it.
So interestingly, I can
actually
chime
think
in
of-
on this.
I was about to say, I can
sorry.
actually like say that like this is exactly kind of how Prusa has worked. They got a name for solving a bunch of problems that were endemic with software and having the best in class software, and they charge $1,000 a printer. And you can buy an Ender 3 for $300, a third of the price, similar almost identical construction, but without some of the bells and whistles that make it truly unique from the software side of things. And you get equivalent performance, but it just takes more effort on the end user's part. And Prusa makes it, they got a name for reliability and for quality, and people are willing to shell out 3 times the money for that purpose. It does work. Alex, I'm sorry I interrupted you.
No, we just started talking at the same time. I was going to say that this is basically, whether it was intentional or not, is what happened to the Boosted board for the electric skateboard brands. Boosted was one of the first real big name brands in electric skateboards, and for a few years they had this absolute supreme reign over electric skateboards until a bunch of Chinese manufacturers started just picking them apart and just undercutting them. And although you can buy very cheap electric skateboard alternatives, because it is a safety concern, Boosted still has that big brand name in having very structurally sound skateboards, even though they are at a much higher price range. So I thought that was an interesting real world example of this.
Yeah, I think you've also seen it with e-bikes as well, not just the electric skateboards. You've seen it with the electric bicycles as well. I don't know the brands, but I know that there are some that are just lights out better, and they don't fall apart.
Our very own Leo actually has some experience with that. He created his own e-bike.
Yeah, I have my own. I made my own electric bike, and
Nice.
it's been standing since sophomore year. So shout out to Amazon.
Success.
Yeah.
So let's go back to the mech lab. Let's pump out 100 of these and let's keep going.
Good luck.
Well, as time approaches to move on to the next group, I just want to say, great presentation, guys. Thank you very much. And you did a fantastic job this semester. And I think, as you progress through the mechanical, or I guess in the case of this one person, aerospace tracks at UF, everyone dreads having a group in a project class setting that is just completely dysfunctional. And I'm sure all of you have horror stories of, oh, the rest of my group didn't do anything and I completely carried that project by myself. But at least from what I've seen this semester, you guys generally had a pretty solid, coherent group. And so I just think that's really awesome. And good job this semester, guys.
Thank you.
Thank you.
Thank you.
Good job, guys. Congratulations.
Thank you.
You made it through.
Thank
We
you
couldn't
very
have done
much.
it without you three. You guys all helped us a lot. So thank you.
I just yelled at you guys. You guys did all the real work.
It was very helpful.
Yeah, I'm taking 2/3 of that credit.
Very good. Okay, well, yeah, for sake of time, let me hit the record button so that we stop recording.